Hi guys, in this recitation, we will be going through RNN basics, a little bit of LSTMs, GRUs, and the equivalent PyTorch code. This recitation will be extremely helpful for homework 3. Before we start our discussion about RNNs, let's talk about the kind of data that we'll be using as input for RNNs. We'll be working with sequential data in which inputs are dependent on one another. As you can see, there are a bunch of examples given on this slide. Let's consider a poem by William Shakespeare. If you just consider one word from the poem, it doesn't really make sense apart from the actual meaning of the word. In order to understand the poem, you'll have to consider a phrase from the poem or consider a poem as a whole. So each input is kind of dependent on other inputs as well. Other examples of such data are audio signals, where the amplitude varies with time, or video data, which consists of a sequence of image frames. And other examples are stock price data, and daily temperature, etc., where data varies across time, hence the name time series data. We have different kinds of data, but each type of data needs a specific type of modeling. So these are the different types of modeling that are standard for such problems. The first category is one-to-one, where we have a single input and a single output. An example of this case is image classification, where you're given one image as input, and you have to classify whether it is a dog or not. The next category is one-to-many, where you have a single input but a sequence of outputs. A good example of this category is image captioning, where the input is an image and the output is a sentence describing the image. The next category is many-to-one, where the input is a sequence and after analyzing the input sequence, the model produces one output. A good example for this case is sentiment analysis of movies, where input sequence corresponds to the movie review. In this case, the movie review is for Batman 2022, and the output is whether the movie review is positive or not. The next category is many-to-many, which can be of two different types. The first one is where a sequence of inputs produces an output only when all the inputs have been processed. An example for this is machine translation, where you produce the translated version of a sentence only after processing the input sentence completely. The other kind of many-to-many modeling is where each input at a particular is. So in this type of modeling, for each input at a particular time step, you have the corresponding output as well. A good example for this is object tracking in videos, where processing a particular frame of the video gives you the location of the object. And in order to track the object, you need to know this location for the next frame as well. So you can watch the video on this link on object tracking. Now let's take a look at what recurrent neural networks are. RNNs are looping networks that share parameters across time, and to learn the parameters of such a network, we'll be using backpropagation through time. It'll be easier to understand if we unroll this network. This is basically the same diagram that is unrolled across time. A point to note is that each column shown here, the x0 column, the x1 column, the x2 column, all these columns share parameters. That is, parameters corresponding to column x0 are the same as the parameters corresponding to column x1, and so on. And the intermediate output produced from the x0 column, that is at time step 0, will also be passed as input to the x1 column, that is at time step 1. In this figure, you can also see that for each time step, an output is produced that is denoted by h, and this output is produced for each time step. Also, you need to have an initializing hidden input as well in order to maintain this pattern, which is usually an array of zeros. Now, for training this network, you'll be using backpropagation through time, where the loss computed at time step, say t, will be backpropagated through time all the way till the first time step, or in this case, the 0th time step. And that's how you perform backpropagation through time.
We have seen that RNNs have issue retaining memory, And one of the reasons is exploding gradients as well as vanishing gradients. So what happens is the gradients don't really translate through the layers down to the bottom, and a lot of the gradients effectively go down to zero, and most of them go down to zero, and some of them actually go up to really high values, effectively not allowing the network to learn. Some of the factors that govern the retention of memory in RNN are the weights in the recurrent network. So you know that weights with singular values which are high sort of shoot up, and the others which are low go down to zero. Along with that, we have the bias of the recurrent layers, the activation used, because we're effectively looking at the gradient of activation. And these are some of the factors which affect the retention of memory in RNN. Now, we would like to ideally have some sort of memory which moves over across the dimension. So horizontally, you could think of some sort of memory which is moving around, along with the hidden states which are being passed, just like they did with RNN, and the input state. And for that reason, we have this variation called the LSTM cell, which is the long short-term memory cell. So you have the cell state, the previous cell state, the previous hidden state, which are coming in along with the input. And you would ideally want to return this hidden state, which is also the output, and the cell state. The cell state can be thought of is also called the error state carousel, and can be thought of as the memory. And you would want to update this as well as the hidden state. And the way this error state carousel is updated is using these gates, which is the forget gate, the input gate, and the output gate. The forget gate takes the hidden state from the previous value, from the previous state, the cell state from the previous state, and the input state at the current time step, multiplies it with the weight, and adds a bias. And then there's a sigmoid, so effectively constraining the output value. You also have the input gate, which is again the previous cell state, the previous hidden state, and the current input, and the input bias. You can think of the input gate as a way of basically figuring out what information in the current cell is of use, and you could also think of the forget gate as a gate which figures out how much information from the previous state is of use. So that, and you have this cell, the cell value, which you get using the previous hidden time step and the current time step, plus a bias value. But the thing to note here is it's a tangent activation, so it's -1 to 1. And you use this cell state along with the forget and input gates to get the new cell state. So basically, what you can think of is you're finding how much of the information from the current time step and how much from the time step before. So basically, how much of the information that's coming in from before and how much is the current information. You're taking a linear combination of them and trying to figure out how much of that is of use. And that's basically what is passed on in the future. You use that value, the current cell state, along with the previous hidden time step, hidden state, and the current input state, along with the weight vector, plus a bias vector and the sigmoid function to get this output cell. And now using this output cell and the current cell state, you get the current hidden state, which is also passed down as the output and is now passed to the next state. Now there are multiple variations to this LSTM cell. So if between these two, you can see that this is something called a peephole connection. This peephole connection doesn't really feature in this second variation. However, because there are so many variations, there are different implementations, but what we have noticed is it doesn't really affect the final output as much. However, we'll be focusing on this implementation because it's closer to the PyTorch one, and we'll now look at the PyTorch, the way you would want to code up a LSTM cell using PyTorch. So this will be useful for your homework part 2. So this is the rnn.lstm. So this is torch.rnn.lstm. You're basically initializing it. You have the input size, the hidden. Let's look at what these actually mean. So the input size is basically the number of features in your input variable. The n hidden is basically the number of features in your hidden state. The number of layers is basically the vertical stack of layers that you have in a LSTM. It's similar to what you would have with RNN. The out size is the features of the output. So you initialize it using the input size, the hidden features, the number of layers, and batch first equal to true. So batch first equal to true ensures that the LSTM cell effectively treats as the input coming in, knowing that the first shape, the first dimension of the shape is effectively the batch size. So it's not true by default. You should set it to true if you would want to implement it like that. This is actually of use for homework 3 part 2. And the way the example here is basically you have a LSTM cell, and then on top of that you have a linear decoder. You could think of it as a decoder. That's what you'll have in homework 3 part 2 as well. And that takes in the number of hidden states from before, because that's the number of features that you have. And the output size is 1. So the network input size would be batch size, sequence length, and the num features. So sequence length would be whatever your sequence size is. So if it's 10, 15, 20, whatever that is, you put that in. The number of features in this case is 1 because our input size is 1. The LSTM output size will be the batch size. The sequence length, again, whatever, it's the same sequence length. This is of importance. And the hidden size, so the hidden features, hidden feature size. And the input shape now becomes, now since you have a sequence of batch size and batch size times sequence length, you basically multiplied that out to get the number of inputs that you're getting. And the hidden size is the feature of each input, of each input element. So you have batch size times sequence length, number of inputs, and the feature size is hidden size. And then you take the linear output as, again, batch size times sequence length, because that's the number of inputs you're passing in, and the output size. So in this case, it's 1. Okay, so there's some things to notice here, which are of particular interest to us, which is, so you've defined it the way you wanted to, just the way we had done it before. The important thing here is, so what is this? What is WIH, WHH, bias IH, and bias HH? What are these, and how do we interpret these dimensions? Which version of the LSTM this is? So, and how do we initialize this? So let's look at the way PyTorch implements their LSTM from their documentation. So this image is directly from their documentation. So you can see that WII is basically the weight that is multiplied with the input, and and then BII similarly, and BHI. WHI is the weight that is multiplied with the hidden state coming from before for the input state. Same goes, you have the forget gate. Instead of the CT tilde that we had, they represented as GT, but the functionality is similar because that's how they're using it to get the cell state. So now, trying to answer these questions, let's look at this example, this implementation, and try to figure out what the answers would be. So weight IH is for the input weights and hidden weights, just as we see it, just as we've seen here. So 16 here is, you can think of it as the batch size, and since it's IH, which is here being multiplied with the hidden state, it's actually 1 because that's what the dimension is. And then the hidden weights. Now, if you look at the hidden weights, it's my bad. Yeah, if you look at the hidden weights, it's actually, see you have 4 of those, and that's why you have 16 cross 4. So this is something to note here. Because you have 4 of those, you end up having a size of 16 cross 4 because of these 4. Now, which version of LSTM this is? This is the Wikipedia version, no peephole connection. One more thing to know is this is, you could actually use torsion.lstm to make the bidirectional version of this also. So you should look at the documentation for that. And initialization. So if you want, you could initialize the weights with some known routines such as Xavier and Kyming, the ones that professor has discussed. And yeah, so now let's look at the performance per LSTM component. So this is to really figure out why is it that we are doing these things? Why is it that we even look at these gates? So why do we even use this forget gate? Why did we come up with the input gate? Why did we use it this way? RNN sort of made more sense because you understand that because it's sequential and you don't want the weights to be increased depending on the input, you sort of make it that way sequentially. But why this complicated architecture? So if you people have actually done empirical studies on that, and if you closely look at this graph, you actually see that if you say look at the no forget gate situation, so it's NFG, yeah, so the no forget gate situation, the error rate actually increases without a forget gate. So based on empirical studies, it's been shown that the current implementations and their variations are actually quite good. And we will be using it in homework 3 part 2 to solve things which we have done in homework on part 1, but more effectively. So yeah, so this is like, this is basically the variations being tested on different architectures and what the accuracies were.
Hi guys, so in this section, we'll be talking about another variant of RNN, that is GRU, which stands for Gated Recurrent Unit. Now, you've learned about LSTMs earlier, but the problem with LSTMs was that they involve a lot of computation. GRU is just a simplified version of an LSTM, which is significantly faster to compute. Let's see how it works. Now, in the GRU cell given in this figure, RT represents the output of the reset gate. This allows us to control how much of the previous state we want to remember. But the key difference between an LSTM and a GRU is that in a GRU, we combine the input and forget gate into a single gate called update gate. In this figure, ZT represents the output of the update gate. This gate allows us to control how much of the new state is just a copy of the old state. So if you look at the equation, if you look at the fourth equation for calculating the hidden state at the current time step, 1 minus ZT represents the amount that we want to remember from the previous time step, and ZT represents the amount that we want to obtain from the current augmented hidden state. This way, we can get rid of an extra gate and a lot of pointless computation. And you can see that the number of equations that you have to deal with in GRU is also less compared to an LSTM, and you get comparable performance as well. In fact, in some cases, GRU works better. But when I was learning about RNNs, what I was most curious about were the cases where GRU does not perform better than LSTMs. An example of such a case would be unbounded counting. It turns out that GRUs cannot count, but LSTMs can count. This is because if you look at the equations of GRU, the tan h in the third equation bounds the value of ht tilde between -1 and 1. And also, since the value of zt is between 0 and 1, because this is a sigmoid, when you tie zt and ht tilde together in the fourth equation, the value of ht also becomes bounded between -1 and 1. That's why GRUs can't perform unbounded counting, whereas this is not the case in LSTMs, where the cell state value, that is CT, this value, CT, can be unbounded. You can refer to this paper at the bottom of the slide to see how LSTMs perform counting. And you can also refer to this paper to see how GRUs cannot perform unbounded counting. Another variant of RNN is a bidirectional RNN. Such networks are useful when you have access to future data for making predictions at the current time step. This figure shows a bidirectional RNN block. As you can see in the figure, within this block, we have two networks, a forward net and a backward net. Now the forward net is represented by the network at the top of the block with the initial value as HF-1. This network processes the input data from time 0 to time t, whereas the backward net with the initial value as HB infinity processes the data from the end to the beginning, that is from time t to 0. Now the final output of this block is a function of the output of the forward net as well as the output of the backward net. Typically, typically the computation performed by these two networks is concatenated to form the final output, but other aggregation techniques include adding these two outputs or taking the mean of these two outputs. In the actual network that is developed by using bidirectional RNNs, you can have stacks of these blocks followed by an output layer. The output layer is represented by these yellow boxes. Or you can have a single bidirectional block in which the forward net as well as the backward net have multiple layers. In this case, the bidirectional RNN becomes a little more complicated.
So moving forward, let's look into some language modeling code. So here we'll be working with character-based language model. So in this modeling technique, this is particularly a many-to-many modeling technique. And I think you guys have gone through this in the lecture as well and in the previous slides as well. So the data that we'd be using here is Shakespeare's data. So it contains some of the poems and texts from Shakespeare. And let's get started. So looking into the code, the first cell basically contains all the imports that we'll be requiring. So we import RNN, we import dataset data loader, and we also import the Shakespeare data. So we'll be providing you with all the data and this particular notebook as part of the recitation. Yeah. So moving forward, let's take a sneak peek at the data that we are using. So here we first load the data and then print some of the statistics of the data set that we are using. So I print the 200 characters, the first 200 characters and the last 50 characters. So if you see here, this is a section of some poem from Shakespeare. So we see that the total number of characters that we have here is around 5.5 million. And unique characters that we have is around 84. And if we see the shape, then it's of a single vector of this particular shape, right? Printing the first 17 characters as indices, we see that these are the indices and the characters themselves are as follows. So 1609/n space THE space SONNETS. And if you print it as text, then this is what we have here. So one thing to note here is that the length of these texts is of variable length, right? So 1609 is of length 4, and then this is of a different length, right? So just keep that in mind as we move forward. Okay, so next, we look into the dataset class. So we have defined a dataset class called text dataset here, and it has three functions inside it: the init function, get item function, and the length function. So one thing to note here is that we have defined sequence length of 200. So why so, right? So as we saw, the data that we had was of this particular shape, right? And we also saw that if we separate it as lines by just separating at /n, each line is of different length. So what we are doing here is we have defined a sequence length of 200, and what that means is we'll be transforming this entire raw text that we have as a set of sequences of fixed length of size 200. Right? So if you see here, what we are doing is we are defining self.data as a tensor, which would be of shape number of sequences cross the sequence length. Right? So what does the get item do? So get item basically gets one of the item from the data that we have defined here. Right? And what would our input and the labels look like? So as we mentioned, we are working on a many-to-many kind of modeling technique. So just to give an example, so say the reference word that we'll be working with is just apple, right? So what we are trying to do here is, say we provide the sequence as APP, right? The first three characters of word apple, right? And we are looking to predict the next character, which might possibly be a L, right? And in the next iteration, we give APPL, and then we want to predict E as the output. So, so if taking that example into consideration, what we are defining the labels here as are, the labels are basically the input sequences, which are shifted by 1. So, so if you see here, the input that we'll be giving is, again, taking the reference word as apple as an example. So the input that we'll be giving will be APPL, and APPL, and the output that will be, the label that we'll be giving is PPLE. So essentially, given A, predict P, given P, predict another P, right? So since we need to predict the next character, we are basically shifting the sequence by 1 and giving that as a label, right? I think that might be clear now. So we are also defining a collate function. So this collate function essentially will be used to transform the list of sequences into batch, and this will be used by the data loader. So let's define the character language model now. So in the init function, we have the vocab size. Now, since we have a character-based language model, so the vocab size will be equal to the unique characters that we are working with. So that will be 84 in this case, as we saw the number of unique characters is 84 in this data set, right? We have embedding size. So if you see here, we are defining self.embedding, NN.embedding, vocab size, embedding size. So why this embedding layer is there? So basically, for all the sequences that we have, right, we'll be passing those sequences through this embedding layer. And what we are essentially trying to do is trying to map this sequence to a vector space and form a vector representation which particularly which preserves the entire meaning of that particular sequence, right? And essentially preserves the semantic meaning of the sequence of the particular sequence, right? So we give a embedding size. So the embedding layer will be basically taking in the vocab size and the embedding size, right? And these two parameters, let's go over the RNN definition, and we'll also cover these two parameters. So we are particularly using LSTM here in this particular example. You could also try using GRUs instead, or yeah, you could go forward with LSTM when playing around with this code. So this particular LSTM will be using the output of the embedding layer that we have defined. So the input size for this LSTM will be the embedding size. What is hidden size and number of layers? So first, looking at num layers. So say if our num layers is set to 2, that means that we are stacking 2 layers of LSTM one over the other. So here num layers is basically helping us define a stacked RNN architecture. So what is hidden size? So hidden size basically defines the number of features in a particular hidden state, right? So defining this RNN, these are the parameters that we specify, and the next thing that we define is a linear layer, which basically takes the output from the LSTM and then projects it to the vocab size. So this is a projection layer essentially. Moving to the forward function, we get the sequence batch and pass the sequence batch to the embedding layer, and the embedding that we get is passed through the RNN that we have defined above. And output of the RNN is basically flattened first. So this output is flattened and then passed through the scoring function, the projection layer that we have defined. And this is basically returned, right? And let's look at the generate function. So why do we have this generate function? So this generate function essentially performs a greedy search to extract and return words. In our case, it would be characters because we are working with character-based model, right? So we have defined like a generated characters array, right? And so we get sequence and number of characters as the input. So just to give an example, say our sequence that we have given is, again, taking the reference word as apple, right? So if we have given sequence as APP and we have told that the number of characters is 2, then we might be predicting two characters after, we will be predicting two characters after APP, and we hope that we predict LE, right? So APP and then we predict LE. So that becomes apple, right? So that's what these parameters are, right? So the initial sequence and the number of characters to be predicted using this particular sequence, right? So what we do is we first take the sequence and then get the embeddings, pass that to the RNN layer, and then the output from the last layer of the LSTM is passed through the scoring function. And then we take a torch.max on all the scores, and that basically gives us the character with the highest probability, right? The highest score. And yeah, that becomes the next character that is predicted using this particular sequence. But what if we want to predict not just one character, but more character, right? So if the number of characters that is to be predicted is greater than 1, then we run this particular code in a for loop. And what we give is, other than the sequence, we are particularly giving the predicted character as the input to our embedding layer. And then again, the story continues, right? That embedding is passed through the RNN, and then output of the RNN passed through the scoring function, and the next character is got. And then that next character is appended to the generated characters list. So we keep doing this for the number of characters that need to be generated, right? So that is what the generate function is doing. Now let's look at the training function that we have defined. So I think everybody will be very familiar with this code doing homework 1 P2 and homework 2 P2. So here we have defined cross entropy loss, right? And for so this particular line takes in the training data loader, and for each batch first puts the input to the device, the targets to the device, and passes the input to the model, and then gets the output, and computes the loss between the outputs and the targets, right? And that loss is back propagated, and we step the optimizer, right? So this is our entire training function. And similarly, we have also written the code for validation. Now let's see how we have, what parameters have we given to the language model that we have defined. So we initialize the language model with character count. So this is the vocab size. So since we are working with the character-based language model, we have defined character count as our vocab size, which will be 84 in our case, right? We have the embedding size of 256 and hidden size of 256, and we have a number of layers as 3. So it's a stacked RNN architecture with 3 RNNs, right? We put the model to device, and we have defined the optimizer as Adam, and we have defined a particular split as follows. So using the entire data that we have, we split it into train data and validation data, and define the train loader and validation loader. So one thing to note here is that we have specified the batch size, and we have also given the collate function, which I had mentioned that would be used for creating batches from all the sequences that we have defined. So doing all of this, we run 5 epochs and train the model, giving the train loader and the val loader. And after training the model, I have written a small function for generating the next characters. So this basically takes the sequence, whatever we want to give to the model, and the number of next characters to be generated, right? And we get the output. So let's try to print something. So we call the generate function with the model and this particular sequence, to be or not to be, that is the Q. And we say that we want 8 characters to be generated. So we see that these are the 8 characters that are generated, and this particular quote makes sense now. To be or not to be, that is the question. That's a popular quote from Shakespeare. Just trying out another sequence and generating n characters. So this output, I don't know if it makes sense or not, but yeah, the model outputs this, right? So before finishing our recitation, I also want to mention that after going over this particular code that we went through in the recitation, I would also recommend that you go over the packed sequences code that we have here. It is very similar to the code that we've gone through. One of the few of the differences that you would see is something's called packed sequence, pack sequence, etc. And what are those? So I will give a very brief introduction just in words. I would recommend everybody to go through this, and more of this would be covered in the homework 3P2 recitation. But yeah, essentially, here we had defined in this example that we worked through, we had defined the sequence length to be a constant of 200, right? And we also saw that each sentence in the text was of variable length. And we randomly, not randomly, essentially we just did a hard split of 200, and that particularly has some disadvantages. So say if we had a sentence of size 2 uh, 2 words, say 10 characters, and sequence length was 15, and the second sentence which followed had 20 characters. So by doing a hard split, we are kind of breaking the sentence in between, and that might lead to loss of information, right? When we are putting that through an embedding layer, we might not preserve the entire meaning of that particular sentence as it is, right? So what we do is we want to kind of preserve the sentences as it is, but we also have a problem that the sentences might be of variable length. And we also know that while batching, we want all the items in a particular batch to be of same length. So essentially, Torch gives us capability of padding the sentences which might not be of this, which might be of lesser length than the longest sequence in our batch, and we can pad it with zeros or any other character, right? And it gives us capability to pad and pack the sequence and pass it through the RNN. So yeah, so essentially this piece of code that we have given here walks through an example of how to pad sequence, how to pack sequence, how to pass that sequence through RNN, and then again how to unpack and work with it, right? Please try to go over this code, and more explanation about this will be covered in the homework 3P2 recitation. That's it for today. Thank you.